The title is Inducing Robustness by Controlling Surprise Relative to a Reference Model. That's going to be really the bottom line. This is about how people deal with learning under risk and uncertainty when the environment is not stationary and may change. And so this gets us into engineering, but I'm going to talk a lot neuroscience because I got into this through neuroscience, not directly through engineering. All right, so this is actually based on manuscripts that we're working on. One manuscript is already finished, but two manuscripts with people here in Geneva, actually. Kirsten Prof, my former student, Fabien Picard is a neurologist, Lina Suter, Tony Berada, Giuseppe Gazio. And then I'm working on the experiment I'm going to talk about, which I didn't talk about in Dublin, with Chia-Ying Pei and Te Bao in Singapore. Pei is a postdoc now in Cambridge. So I'm going to talk a little bit about economics and finance, but I think, even if you come from this with a psychology background, I think you should understand a little bit that economics is not monolithic, and finance is this strange part of economics where not only do academics make more money, even more than economists, but also it actually has it has a completely different view on the world that economists are not always aware of. Of course, that gets to neurofinance as well. I'm going to very briefly give examples of neural signals correlating with risk and risk prediction errors, because this is how I started in neuroscience. And I've always puzzled why actually we see what we are seeing. And then neural signals correlating with uncertainty in support of reinforcement learning. So that was actually basically a part of machine learning and so, but applied to the brain. Then I'm going to talk about hardcore neurology, ecstatic epileptic seizures, which is a very strange phenomenon. And then finally, I'll get to the main point, which is robustness and control theory. Okay, so there's a lot of stuff to be covered here. I'm going to try to focus on a few things and then leave the details for another time. Right, so first, economics. Economics is, and many other disciplines, are now based on actions are taken to maximize expected value. And I do understand that some people say actions are taken as if people are maximize expected value. Let's not distinguish these two things. So the whole idea is that people maximize, optimize, and we can talk about value, utility, and reward depending on what field you're talking about. And in neuroscience, they prefer to talk about reward or value. In economics, it's utility. Optimization is central here. Okay. If you get into risk and uncertainty, which is really what finance is about, then you're told, if you're an economist, oh, well, that's very simple. If you want to take into account uncertainty, you just go to expected strictly concave utility. Risk-averse behavior is a result of diminishing marginal utility. I have plotted here the typical strictly concave utility function, and the expectation of a gamble has a utility higher than the gamble itself. So as a result, if the machine is to behave in a risk-averse way, you ensure the rewards are valued with diminishing marginal utility, and lo and behold, the machine, the robot, the whatever algorithm you're using will actually behave as if it does not like risk. There is no need, as a result, to explicitly account for risk and uncertainty, right? Which is actually interesting to see whether there are risk signals in the brain, uncertainty signals in the brain, which actually drive choices. And the answer will be yes. And believe it or not, when I started doing this around 2000, 2003, there were some, well-respected neuroscientists and economists that told me you won't find anything for exactly this reason. This is, of course, wrong. And that is really the theme, okay, it's wrong, but why is it wrong? So let me tell you a little bit of finance. When you study finance, really your finance is split off from economics is where it actually started dealing with uncertainty and risk separately from expected reward. And the most famous case was Markowitz, Harry Markowitz, the late Markowitz, who developed mean-variance portfolio theory. And then later on the capital asset price model and multi-factor models, which are widely used in the industry out there, partly out of practical. concerns because finding an optimal portfolio with, let's say, locked utility is just impossible, computationally. So, but it turns out mean variance analysis is actually really easy. So you separate expected reward from risk being variance. In derivatives analysis, the Black-Scholes model, I just put the formula there because it's a fancy formula, right? In the Black-Scholes model, option value is determined by uncertainty volatility only and not by expected return. Expected return, if you actually look at the formula, you'll see there is nowhere a parameter for expected return. It's only risk. And risk management as a result has become the key of finance in the industry. This model is used widely, or derivatives of it. Modeling volatility through gauges has become extremely important. And then actually what was really the crown on the work was that many assets can be priced merely by assuming absence of arbitrage. This is called fundamental theory of asset pricing. Under absence of arbitrage, this is how you price everything. It's the core result in mathematical finance, and as a result, when I was 23 years at Caltech, and I had all these students from the sciences and math and engineering in my class, and they didn't need to know any economics, no demand functions, no utility functions, nothing like equilibrium. Don't worry about this. I'm not going to teach that. I just need you to understand absolute arbitrage. So it's a very, very different field. It has become a very different field as a result. There are still there are touching points, but what's crucial in finance is management of risk. And I come out of that field. I go into neuroeconomics, and I listen to my colleagues Antonio Rangel and Paul Glimcher, and so talking very enthusiastically about value and utility. And I said, well, what are you talking about? So that's historically a little bit where we should position things. So finance focuses on management of reward and loss, risk and uncertainty. So neurofinance actually is, of course, an outgrowth of that. I'm not going to talk about the following slides. What is risk and uncertainty? It depends on whom you're talking about. In economics, actually, risk is extremely well defined. It's something that you can write down the probabilities of, and uncertainty is ambiguity or Nietzschean uncertainty. In neuroscience, risk has many, many different shades. What we call risk in economics is called expected uncertainty in neuroscience, in computational neuroscience. Unexpected uncertainty is really more to do with ambiguity. And then we have also surprise and expected surprise, which comes actually out of computational neuroscience. A part of computational science, neuroscience that has had less influence from economics and neuropsychiatry. And I'll come back to that later. So it's a zoo out there. I'm going to try to make precise what I mean with risk and uncertainty and surprise and expected surprise as I go along. All right, so that's what is risk and uncertainty. So let's first talk about neural signals correlating with risk and risk prediction errors, but not with reward. I just want to give you two examples of risk signals in the brain, and in particular in a brain structure that, as you'll see later on, is extremely important for awareness, consciousness, who we are. Do you realize that you are separate from the rest of the world, etc., that you're an identity, but also feelings, emotions, introspection, and the like. And in that particular region of the brain, there are basically only uncertainty signals. There are no reward signals. And as I will show you later, in traditional accounts of the reward processing system in the brain, the dopaminergic system, it doesn't even fit in there. Usually it doesn't even show up. I'll come back to that later. So here's the first example. This was by Martin Paulus already in 2003. And you can see what happens. So this is the beginning of neuroeconomics, and Paulus completely ignores utility and all that stuff, and he's talking about an experiment where all the possible options have exactly the same expected reward, but there are only different risks. And then he shows that when there is differentiation in risk, you have activation in this region that you see. I don't know whether you can see my cursor on the brain picture. This gray area, cortical area called the anterior insula. The insula is a region that lines this part of the cortex, and it's the frontal part of it, the anterior part of it. And you'll see I'll talk a lot about anterior insula. It's become my favorite part of the brain. And what's interesting about this is it's not brought in connection with choice and uncertainty, numeric and economic choices, but actually with psychopathology. If you look at the panel to the right, you'll see that the signal difference in anterior insula is correlated with both harm avoidance and neuroticism, a Z-score, typical clinical psychology score. So that literature branched off and is almost never crossed really with neuroeconomics, with what the economists have been doing, because it's actually more interested in psychopathology, and it doesn't talk about reward. It only talks about risk and uncertainty. It's as if reward is not really important to understand psychopathology, right? And Paulus has several papers on this. So that's an example. Here's another example. By the way, before I start, this is the location of the anterior insula. It's the red arrow there, actually before, in front of the red arrow. So anterior insula. So this is a picture of a cross-section of the brain from the back on the left-hand side, caudal, and the front, anterior. At a cross-section about just a little bit left of your eye. And then you can see this part of the cortical structure that's inside, and thank goodness it's inside, because it's extremely important for, as I mentioned, awareness, etc. Right, and so we're talking about the anterior parts here. The posterior parts are more involved in relaying emotions and so on to the brain. So bodily, what they call the autonomous neural system. Of course, it's not autonomous, but they used to call it. They still call it like that. Relaying that to the brain and actually the other way around. Okay, so that's anterior insula. I'll come back to that later. So here's an example. This is what I did with Kirsten Preuschel very early on. You see 2006. We looked at a card game. If you look at the right-hand side, it's basically a deck of cards, and we pull cards from the deck, 2 cards from the deck, and the people have to guess whether the second part is going to be higher or lower than the first part. But every time you pull a card, there is a change in the expected reward. There is a change in the risk. And in the middle, you see activation in anterior insula as a function, in insula, actually, in generic, anterior insula as a function of the probability of reward. And as you can see, there's this very nice inverted U-shaped function, which you could call entropy, but you could also call it variance, variability of the payoffs. There is no linear relationship with reward probability, so there are no reward signals in that part of the brain. And you can actually distinguish, as you can see on the right-hand side, 2 signals there. The one that's more caudal, so higher up, is risk prediction. It's predicting this is the risk that's going to be resolved when the second card gets pulled. And then you have underneath it, so more ventral, the risk prediction area is there is an outcome. I expected the risk to be so much, and it turns out it's higher. The realized risk is higher or lower. So that's a signed effect. And this has been very, very well replicated over and over again. This part of the brain is involved in not only anticipating risk, but also in learning of risk. That is, there is a risk prediction error, right? And the interesting thing was that this is in a part of the brain where there are no reward signals whatsoever. This part of the brain is extremely important, again, for psychopathology, but also for things like, as I mentioned, awareness, sympathy, empathy, and, for instance, chronic pain. If you suffer from chronic pain, the key of your awareness of the pain that's happening is exactly here in this part of the brain. So what do we conclude from these few slides? Like the discipline of finance, the brain appears to pay attention to risk and uncertainty separately from reward and value. So there's separate encoding of risk versus reward. and it's in separate brain areas, anterior insula. Doesn't mean that it is completely split off. Actually, you have risk signals in reward signals, in reward structure of the brain as well. So now let's talk about, for a while, what I did after finding this, we basically sat down and we thought, why is it there? Well, let's think about it. The economists say you don't need these signals to make choices, so maybe they're actually there to help machine learning, to help reinforcement learning. Because in machine learning, in reinforcement learning, there's a learning rate. And the learning rate, if you want to emulate Bayesian learning, so a very efficient way of learning, you have to adjust the learning rate depending on the uncertainty in the environment. And so to make a long story short is, yes, actually, there is now extremely convincing evidence that this is exactly what some of these risk signals do. And I'll give you an example here. I'm not going to go into details here. This is a paper that we published in Neuron with my former student, Lise Payson, and John O'Doherty at Caltech on risk signals in a multi-arm bandit problem, a restless multi-arm bandit problem. So this is an environment in which these rewards may change. You have contingency shifts, and it turns out the chance that there is a contingency shift is among others encoded in part of the brain stem. See a beautiful picture of the brainstem here on the bottom right side. You see the cerebellum behind it, right? And it's where norepinephrine neurons are, noradrenaline, which means these are attention neurons, etc. Later on, this has been replicated with pupil dilation because it turns out these neurons are directly influencing pupil dilation. And so that means that actually uncertainty is there to actually support a learning of the same type that is being used in machine learning. So 2D learning, Q learning, etc. So all that stuff. But that was not sufficient for us because it's still, we had also shown with Wolfram Schulz's lab in Cambridge that in fact the fMRI signals that we see in anterior insula are causal for risk aversion. So there is it's not just learning, it's also the choice. And then the question is, what is it doing? So interim conclusion, one role for separate encoding of risk and uncertainty signals is to support reinforcement learning. Right? So modulation of the learning rates in the changing environment and emulation of Bayesian learning through delta learning or TD learning, it's generic machine learning. Leading a lot of computational neuroscience to call the brain a Bayesian brain. Not using Bayes' law, but using TD learning, delta learning, to emulate a Bayesian learning. And for that, you need all these risk signals. So that was very nice. Has little to do with neuroeconomics. The neuroeconomists are usually not aware of this. It's more computational neuroscience. And then, as I mentioned, neuropsychiatry. So we are looking further for what's happening. And one day, there's a person in Geneva who contacts me, Fabien Picard, and says, well, you know what? I know that you've worked on anterior insula. I have a story to tell you about epileptic seizures, and in particular, ecstatic epileptic seizures. So you're probably all familiar with epileptic seizures. Basically dysfunction of the brain. The neurons start firing completely arbitrary without much control, and it can actually lead to you can die in it if you're not careful about this. Just like with migraine, there's an aura before an epileptic seizure sets in, so actually the patient can predict something is going to happen. Usually this aura is both it gets you in a state of feeling of disgust, but also anxiety and fear. There is one major exception, and these are the ecstatic epileptic seizures. And let me just describe what one of the patients said. So this is from one of the first papers that Fabien Picard and this Bud Craig, who also worked on anterior insula, talked about in epilepsy. So let me just read this because it's interesting to read this. So we have a 53-year-old right-handed female teacher described focal epileptic seizures that began in 2001 as a sensation of warmth filling up her body from her feet to her head. Asked to provide a more precise description of an episode, She explained it was something that I've never felt before. It felt as though my body was filled up with a sensation which was quite surreal. The feeling was almost out of this world. This led to a feeling of complete serenity, total peace, no worries. It felt beautiful. Everything was great. She added, during the seizure, it is as if I were very, very conscious, more aware, and the sensations, everything seems bigger, overwhelming me. Now, this is not a useful description of epileptic seizure. If you have family, if you actually suffer from it yourself, you probably know what I'm talking about. So when asked if it was like an orgasm, she answered, maybe the close sensation that I know would be an orgasm, but what I felt was not at all sexual. I have no religious feeling, but it was almost religious. These episodes influenced her life. It is a big happening in your life to have these seizures. Thanks to these experiences, I do not fear death anymore. I see the world differently. Every sensation is stronger. For instance, I see more color than before, and I have more detailed perceptions, particularly when listening to music. There were no post-ictal symptoms, that is, after the epileptic seizure. Occasionally, these ecstatic seizures were followed by the involuntary repetition of multiplication tables in her head, the typical epileptic results. So this is a description of somebody who says, I have reached my bliss point. And notice that it does not involve reward. It's not that, I feel like I'm Elon Musk, I make a lot of money. It's more like I feel like I'm a Buddhist monk. I feel like I'm in nirvana. That seems to be happiness, and they feel uncertainty, but more control of uncertainty. Now, what does that have to do with anterior insula? Well, so here's another paper by Fabienne Picard on basically doing brain stimulation in order to verify whether anterior insula is really responsible for this. Because with the epilepsy patients, very often, find where the foci are. What they do is they lower electrodes in the brain and they actually go to anterior insula because it is so well connected with the rest of the brain. As I mentioned, actually, it is a region that is considered to be the key to awareness and consciousness. And you can imagine that as a result, it has to be extremely well connected. Amygdala is another region, other parts, anterior cingulate cortex, and so there's a posterior also, but anterior insula is one. And so when you lower nanotones, you can also stimulate the brain. And that's what she did. And she was able, here are 3 patients that had ecstatic epileptic seizure to induce an ecstatic epileptic seizure in these people. So that was the first proof that actually anterior insula has to do with that. And this is the region that actually is not interested in reward, is only interested in uncertainty, as I mentioned. The story is not complete yet. She's been able to induce ecstatic phenomena in non ES or ecstatic epileptic seizures patients. So I'll just read from the abstract. For the first time, an ecstatic experience has been evoked through the electrical stimulation of the dorsal anterior insula during pre-surgical invasive intracerebral monitoring in a patient who did not suffer from an ecstatic form of epilepsy. Of course, this was an epilepsy patient, but it was a different type of epilepsy. You see their brain picture, and you see the electrode in there with the contact points, and it's the red points that you can see is actually sitting at right at anterior insula on the exterior part of it in the gray matter. So what does this all have to do with? Well, there's an emerging theory here that comes there that maybe happiness is a perceived control of uncertainty. And there is in psychiatry an emerging evidence that indeed that is the case. So increased anterior insula activity happens because of probable threats in anxious individuals, right? So this is correlated with diminished perceived control. So on the right-hand side, you can see that as you look at anxiety proneness, you see more anterior insula activation to risky outcomes. That's basically what it is. What they saw probable threats is risky outcomes. And on the right-hand side, you see that the perceived control also is negatively correlated with anterior insula activation. So they feel like they're out of control. Right? So what does that mean? Well, okay, before I conclude with this, let's now link this to awareness. So why anterior insula? Well, as I mentioned, it's involved in interoception. It's a conduit between bodily signals and emotion and feeling. And most importantly, it's actually related to self-awareness. On the top, you see a part of a cover of a book by the late Bud Craig, who was the person who in neuroscience has been advocating this idea that anterior insula is really where awareness grows in consciousness. So it's a book, an interoceptive moment with your neurobiological self. And of course, as I mentioned before, this if you talk to the neurologist, they bring this in association with some Buddhist theories. Peace comes from within, do not seek it without. I should add to that that awareness itself is recently in neuropsychology being associated with metacognition. So here we have two people. I bring this up because Ori saw this as well in the speech by Steve Fleming, is on the right-hand side, on the left-hand side here, on where he actually links metacognition to self-awareness, right? Metacognition is basically, am I sure that I'm doing the right thing, right? So there's confidence, etc. And this last several years, quite a bit of research on that. On the right-hand side is Liz Phelps, and she's the person who made a career in understanding the intersection between emotion, memory, and learning. And you see that emotions converge. They converge eventually on awareness. And as you'll we had a little conversation about this during his talk. Steve Fleming admitted that actually anterior insula is really presumably where everything converges, where we are all going to get together. So what's an interim conclusion? Happiness is not the same as maximizing reward and avoiding losses. And again, psychopathology tells you that, right? An important component of happiness appears to be the feeling of control of uncertainty. It's not, I get more rewards. Psychopathology such as anxiety appear to be related to a lack of control of risk rather than the inability to attain reward goals. And this is a very important message for decision theory that puts up first, and certainly economics, that reward is the goal that we want to have, right? Anterior insula is uniquely positioned to play a crucial role in happiness. I'm not done yet. So that's the situation we were in well, maybe 10 years ago, even if some of the results, the evidence, the convincing evidence dated from a little bit later. Let's talk engineering, right? So you go and talk to control and dynamical systems engineers and you ask them, what about control of uncertainty and trying to optimally solve some task? And they will tell you, okay, actually, this is a very large part of robust control. So let's go to adaptation through control of surprise rather than through value maximization prediction error. So let me just step back and say this is the principles of control theory. This is also machine learning, right? And it's the classical neuroeconomic paradigm of how people learn to make the right choices. There is this value function, which is just an expected time separable utility function of rewards. You can make it a utility of reward, that doesn't really matter. And you can write down the optimal reward in terms of a value function as a function of a state. So you can make it telescoping. And out of that came this idea of TD learning. So you update your value of a particular action, a particular state by taking the value that you thought it had in that state. And then you have a TD error that will allow you to update. Right, so there's a learning rate and there's a TD target. And it's by now very well known that the dopaminergic system in the brain is actually doing this, not only in humans, but also in animals, in rats, in mice. And so this is how reinforcement learning actually happens. A rat learns to make the right choices to maximize rewards over the time of an experiment by solving this problem, by applying these algorithms that are now very well known and applied in machine learning, even in large language models and so on. Right? So this is reinforcement. You just have to try long enough. There is no role for uncertainty here. As I mentioned, if you want to make this, if you want to take into account that maybe uncertainty here, you just, instead of rewards, you take a nonlinear transformation of rewards, right? The question is, are there alternative learning procedures where surprise is signal, right? So surprise or uncertainty signal is central, and there is one. This is called active inference. This comes actually out of what happens in the visual cortex. So given an outcome benchmark distribution, you try to find actions that bring the actual outcomes as close as possible to that benchmark distribution. So you minimize expected surprise relative to a benchmark. And the expected surprise here is KL divergence. It's not important if you don't know what it is. It's just basically surprise intuitively. An example of that is gray parrot vocalizations. They perceive certain sounds, a certain distribution of sounds. And what they do is they try to find the right actions, that is, the sounds they produce themselves, in order to, as close as possible, to get to that distribution of sounds that the parrot hears. The parrot, of course, doesn't understand anything. It doesn't see the actions of the person uttering the sounds, because you can't see this. It's inside your body, right? But it manages to do it like that, right? So it's not really imitation of the actions, but imitation of the outcomes, right? So this theory has been associated with a guy in London, Carl Friston. Carl Friston makes a big deal out of it because this may relate to free energy, etc. And let's not get into that, because I want to focus on the expected surprise part of it. So here is where a very different type of machine learning. This machine, the parrot, learns not because it's doing standard, it gets rewards whenever it does the vocalization right. No, just because it wants to imitate this distribution of outcomes. There's a problem with that, of course, as a general theory of how people learn, and that is that active inferences replaces the thing that is to be optimized. Instead of maximum reward, you get minimum surprise, right? And it fails to explain why there's this important brain system that operates on the basis of maximization of reward, machine learning, to the point that active inference may be less important in driving decision making. So in the picture on the right-hand side, you see the brain circuitry that is generally understood to be part of this machine learning brain that we have, the reinforcement learning brain. And you can clearly see, the typical structures. You have the dopaminergic neurons in the ventral tegmental area. You have the nucleus accumbens, prefrontal cortex, amygdala is in there. And I just want to emphasize the complete absence of anterior insula in this, as if it has nothing to do with this, right? And then I just told you that anterior insula is important for choice. We know that, we just don't know how it fits, right? You see risk and uncertainty signals in amygdala that actually do drive this dopaminergic system as well. But where is anterior insula here in this picture? So there's something missing. Once you go into psychopathology, all at once you have to take into account that anterior insula is doing something there. But we need a role for surprise that is consistent with, rather than replacing, the principles of reward maximization. And that's here where the engineers provide you with inspiration, right? Again, I must say, one has to be lucky in life. I was for a very long time part of computational neural systems at Caltech, and there was a bunch of biologists, obviously, neural systems. There was a bunch of computer scientists, but there was also engineers in control and dynamical systems. So you go talk to them and you say, how does uncertainty fit? And the answer is robustness. Okay, so let's talk to the Caltech guys. And here's a result from a paper of Pietro Perona at Caltech that he talked about when he was still working on it. So he was working reinforcement learning in the machine learning tradition. And we know reinforcement learning can be extremely powerful. We now see that with large language models and so, but we also know it's absolutely not robust, right? And the example of that, you can go through the how successful it has been. That's the graphs on the left-hand side, but let's look at the right-hand side. you can learn to machine to recognize cows. If the cow is somewhere in an alpine environment, then basically it's 100%, almost 100% able to correctly classify it. If the cow is on a beach, it drops 3 percentage points, right? When it's when it's actually on a beach together with a bunch of people and a boat, it basically has no capacity to actually recognize there's a cow there. So it's not very, very robust. It really needs to be in a familiar environment. It's optimized for that environment. And as a result, it's not robust. And the question then you ask the engineers, what do you do to make things robust? And they said, well, the classical thing is let's prepare for the worst. But that's kind of stupid, right? So this would be you develop an anti-lock braking system, and what's the worst that can happen? Well, you drive with your car on ice. As anybody who's done this knows. If your brakes would also always work as if you're going on ice, because there could be ice anywhere, right? At any moment in time. It's kind of stupid, right? So what the engineers since the 50s have been developing is so-called model reference-based adaptive control. On the right-hand side, it gives you a schema that works. Let's focus on the bottom half of this. So you have a bunch of stimuli, or this could be a state. So you have detailed trial by trial state description. And then you have a controller. And the controller has an adaptive policy, and it maps inputs into actions. It tries to find an action, and there's an outcome, and the classical control will then go back and maybe just update, right? And there's some parameters there, right? So this is classical control theory, dynamic control theory, with the goal of optimizing. This leads to 3D learning, etc. So all this is very well understood. What does robust control do? It has actually a reference model, and it's going to evaluate how well the controller does relative to what the reference model would have guessed would happen. So if you now go to the top, the same stimuli are processed by a reference control model, which then predicts what the outcome could be ideally in this ideal world. So this could be, you'll see the application later. You're in a Gaussian world where your target moves according to somewhat aggressive process, maybe unit root process, and you want to guess where that target is next. So it moves there. So what do you use? It's a Gaussian world. So what you do is use the Kalman filter. It has a particular way to set the learning rate or the Kalman gain. Can all be predicted, and then basically this is what I predict. The actual world, as you'll see later on, could be completely different, could be non-Gaussian. So you take exactly the same situation, but instead of Gaussian driving processes, you have leptokurtic driving processes like in finance. That is, there are heavy tails and there's peakedness in the distribution. And then these outliers that are very, very frequent, they could either revert or not revert, right? So now you have a reference model that's Gaussian, but the control lives in the real world and is trying to adapt its learning rate. And it will be the reference control model will tell you which should increase or not increase, right? And how does it do it? It tries to minimize the expected surprise. So it looks at the anticipated size of the prediction error according to the model, a Gaussian model, and then sees what the controller can accomplish in a real world where everything is leptokurtic. And when that's too big, that difference is too big, so the actual surprise is too small or too high, it's going to adjust, right? And so you get this red part of the adjustment process, which is parameter adaptation to reduce negative surprise. So if you're interested in that, here is a typical reference, a textbook of it, model reference-based adaptive control. The way you have to think about this is an autopilot and a human supervisor, right? Why do we still need two guys up front in the airplane? Well, the autopilot is extremely good, but it's not fully robust. And as a result, we still want to put some humans in there. And this idea that actually trying to minimize surprise seems to be now getting into cognitive psychology. Here's an example that Colin Cameron is trying to push, neural autopilot theory of habit. You switch between habit and goal-directed a goal-directed choice. This is now evidence for consumer purchases where that seems to be the case. Right? Here's an example of an actual robot that we know is 100% controlled using this model reference-based adaptive control. It's the Robonaut 2 in the International Space Station. A lot of robots out there are controlled by MRAC, but the companies that work on it will not tell you because, of course, that is the key. The software is often the key nowadays of anything working well, right? Whether it's a machine, a car, or anything like that. And software is not something you can get easily a good patent on. So very often it is not patentable. And so it's very hard to get very concrete industrial applications. I know that you talk to the engineers. I gave you the example of anti-lock braking systems. They're working on that on the basis of MRAC. There's also robots, limbs, artificial limbs, also work on that because it makes them smooth, robust to whatever they hit, etc. Anyway, so go back to humans. So this is an example of where we found evidence for MRAC. And involvement of anterior insula. So this is basically, there's a target, a red dot that moves in a circle, and you have to predict where the red dot is going to go next. Now the dot moves like a stock price, so it actually is distribution. It's leptokurtic. You can see underneath the distribution of changes in the location of this dot, and you can clearly see it actually has very heavy tails. But sometimes, in one treatment, the outliers reverse, which is the red treatment, and in the blue one, it's not reverting. And the blue one looks more like a standard common filter, Gaussian common filter, even if the outliers are much bigger. In that situation, people actually behave close to optimal. In the other one, they can't, and they're struggling all the way through. And you can see that from, if you look at the deliberation time, which is the middle plot, in the transitory situation, that is the outliers revert, right? Their deliberation time is long even after the trial, after the outlier, at which point you can predict exactly what happens. And yet they're surprised about this. You can see this also on the right-hand side, their errors, prediction errors are larger. But more importantly, circling back to anterior insula, there is only one part in the brain that actually distinguishes these two, and it's anterior insula. People lose control of, they're much more surprised in that environment where the outliers revert than when they don't revert. And you can clearly see a beautiful picture of anterior insula, bilateral anterior insula activation in the contrast between the two treatments. And that's the only thing that survives whole brain correction. You can also fit a model of reference-based adaptive control to people's choices. And to make a long story short, it fits very, very well what people are doing here, as opposed to the Bayesian model that doesn't fit things correctly. So I'm not going to go into detail here because I want to show some other evidence in addition to this. We also know that from intracranial recording we are now doing in Geneva here, that anterior insula reacts also to surprise that is below the average. Let me show you. This is an electrode connected to anterior insula, and there is a surprise here beginning, and the black line is the highest surprise. The blue line is the middle surprise, and the red line is low surprise. And you see in the first 400 milliseconds, you get a nice ranking: red low surprise. Oh, sorry. Red low surprise, blue middle surprise, black high surprise, and you see the nice ranking in that. After about 400 milliseconds, the only one that really remains high activation is the low surprise. It's the one that actually is most strangest relative to all the theories that we have. And the brain actually then pays attention to that. Right, so low surprise, of course, the way you have to think about this is it looks like people do not like to have surprise, consistently surprised at below what they expected. If they expect uncertainty and they tolerate a certain amount of uncertainty, they abhor less uncertainty. You lock them up like during COVID, right? They start doing crazy things because they need excitement. They need, the brain wants to have that. So that puts a completely different spin on these psychological phenomena that you have when people are bored, which is something that's extremely hard to explain in terms of standard economic theory, except if you just put boredom in utility function as a loss. I don't like boredom, to be bored.
Peter?
Fine. Yes.
Can you go back one slide? Maybe you can go say a couple more things about what's the experiment? So what did the subjects have to do in this experiment?
So
I'm not sure I understand. Yeah.
yeah. Okay. So this is exactly the same experiment as here. So this is a patient, and the patient has to predict where the target is next, right?
Yeah.
And we can measure the surprise relative to a common filter, right?
So you
That
mean
is,
when you're saying surprise below average, so low surprise is
yeah, okay.
relative
So what
to?
does that mean? Yes. So what does that mean, right? So you write down a common filter model of this. Right? But you see down there distribution, you know what the variance is, you know what the mean is, you write down a common filter model and you find the right common gain. Also, you can predict what the expected prediction error is, right? Because that's just standard Riccati equations that you solve. And then what you do is you say, okay, what is the actual surprise? That is, did this target move a lot more, a lot less than this expected surprise? And it turns out that when the target is actually just very, very close, not moving very much, anterior insula is surprised. Right? This is low surprise, actual surprise relative to what was expected. Right? So that's what I mean with low surprise. It's a
I'm
negative risk prediction error, right? So that's basically, take a typical stock price, or the Standard Poor's 500 has a volatility of return of about 15% on annual level. Imagine that one day, the volatility is 25%. The VIX index or whatever they call it is 25%. That means the stock prices move a lot more than you expect. If it's only 5%, then they move a lot less than you expect. And that actually also triggers in the brain. Something is happening here that is not normal, right? From the point of view of control theory, it makes an enormous amount of sense, right? That you also are aware that your environment is different because there is a silence before the storm, right? So to say. And we seem to be very attuned to that. It's not your classical way of thinking about, well, let's be happy that there is not as much surprise. But the brain interprets that being, gee, something is happening, right? And that's what you see here, anterior insula. So when you look at the red line, these are trials where the target didn't move very much and they expected it to move, but just not as much as it actually moved. And of course, it doesn't react very much. That's the implicit reaction. That's the usual. They call this the P300 effect. But about 400 milliseconds into the trial, we know that actually brain starts really processing these signals rather than reacting to them in a very intuitive, instinctive way. And as you can see, it starts thinking about what happens there with the low surprise. Because the other high surprise, medium surprise is medium surprise is what I expect. So, you shut down, you can see the black line drops below the blue line. And then it's the red line, which is the low surprise that actually stands out here for 200 milliseconds. 200 milliseconds is a big, big time, long time in the life of a bunch of neurons, right? So that's what that means. Okay. Lastly, what we did is we tested robust expectations adaptation on 40,000 plus forecasts in self-referential systems. So these were experiments that we didn't do, but that people in Amsterdam, in Singapore were doing, where people had to make predictions about a price. And there was a system that computed the price, gave a feedback. And people were actually making money depending on how close they were to predicting a price. But it was self-referential. So it was a non-stationary system. If you made prediction mistakes and you update your prediction model, you affect whatever the clearing price is going to be. And you can clearly see here The realized market price is the red one, and the prediction for this particular guy is the blue line, right? And you see he underpredicts, then overpredicts, and then comes closer. And we were trying to understand what is happening here, right? Is this adaptive expectations, right? So this is your prediction error. This is the outcome, the price. This is your expectation. There's a learning rate, and you update your prediction. Standard economics. People like Impordalo and Schleifer and so, they have now worked on that. They use adjusted common filters, all with an alpha that's influenced by some psychological factors or so, relative to the optimal common gain. What we did is we actually looked at what would alpha be if this is model reference-based adaptive control, relative to a standard common filter model. And that's where we actually found the following. First, there is this long-standing model in computational neuroscience. If you're in such an environment that's not stationary, you use Peirce-Hall correction. And in that correction, you change your learning rate with surprise. It increases with surprise. It's not a robust procedure because it's maladaptive in many situations, just like when actually outliers revert, right? And as you can see here, this is 0. This is the parameter that explains whether the changes in alpha depend on surprise. Changes in surprise, and the answer is no. Well, there's some evidence in the negative, positive, the mixed feedback models, but overall, it basically there is no evidence and for this kind of very popular model in computational neuroscience. However, there is if you do this computations, what you should be doing under MRAC to minimize expected surprise, what you need is to monitor the autocorrelation of your prediction errors. You write down the optimum. So if the autocorrelation is positive, so my prediction error today is positive and tomorrow it's positive as well, it means I actually should adjust my prediction more, so I have to increase alpha. If my prediction errors are negatively correlated, so after a positive prediction error, there's a negative, a positive, a negative, positive, negative, then actually I'm overreacting. So I have to decrease my alpha, my learning rate. Right? This turns out to be the same prescriptions in Sutton's old paper on delta bar delta. But that basically, his prescription is not on a generic theory like MRAC. And to make a long story short, this is what we find. So this is an example. So what we do here is multi-ordered logit analysis of decrease, no change, and increase in alpha. And what you see here is across these 18 experiments, so each of these experiments is a bar, you see the probability of an increase in alpha. So the theory says that the highest chance of getting an increase in alpha is when there is positive autocorrelation of your prediction error. And then you can see here positive autocovariance, but also when there is a large error. So when the error is large, we see that actually when the error is smaller, you get less of an adjustment. So people don't pay as much attention. So the probability, for instance, here that you get after positive autocovariance an increase in alpha, it's about 70% in the first experiment, and it goes up to 80% in the 12th experiment, right? And then, when the error is small and there's positive autocovariance, it's slightly less. As you can see, it's slightly above 50% in experiment 1, and it goes up to 60% in experiment 12. When you get negative autocovariance, you get the opposite, right? So you get a less than 50% chance of increase. In fact, the probability now goes to the decrease. Right? As you can see, for instance, when there is a large error, negative autocovariance, there is only about a 30% chance of an increase. And so this is exactly consistent with robust controlling engineering. People use surprise and in an optimal way in order to adjust their learning rate. Anyway, so what does that mean? Robust adaptive control can be accomplished by monitoring outcome surprise of a supervisor relative to expected surprise in a benchmark model. And humans appear to change their learning rate in accordance with expected surprise relative to a Gaussian world, where the optimal learning rate is constant. And then, of course, we are still working on does anterior insula monitor this surprise. That's the EEG analysis we're doing in Geneva. In concluding remarks, I think this is what I want you to remember from it. Neurofinance studies the neurobiological foundations of perception and choice under risk and uncertainty. Neural signals correlating with risk and uncertainty are pervasive in the brain, and anterior insula appears to play a prominent role in monitoring risk and uncertainty, and not in reward. They drive not only choice, but they also modulate reinforcement learning. And they may be crucial to ensure reinforcement learning exhibits robustness in accordance with principles of control theory. So that's it. Thank you. There's lots of people because this is actually summarized over 20 years of research. So I see some other names there from Caltech, EPFL, Cambridge, and Geneva. Thank you.
Bossaerts, thank you so much. I hope now I pronounced your name correctly.
Yes, that's right.
At least I tried. Unfortunately, we're running out of time, so those who have to leave can leave now. Thank you again for this fascinating presentation. Those who want can stay for the informal discussion, which will start right now. And those who have questions, this is the time to ask them.
Yeah, I'll start.
Go ahead.
So if you go one slide back to the concluding remarks, that slide. Well, another one actually. Or
was it this one?
Yeah, this one. So humans appear to change their learning rate in accordance with expected surprise relative to a Gaussian world. So is there evidence of that also, where the generating process is not symmetrical, for example, maybe bimodal or something?
No. So as far as I'm concerned, we are just starting this. We chose this particular non-stationary world where you try to follow a target because we thought it is actually natural to follow the common filter, standard common filter ideas. The engineering literature doesn't talk much about what models you should be using. They actually use models that provide stability. And they don't say much about how you learn about these models. So this is a completely open question. How do you form your reference model? The same thing happens in active inference, by the way. What is your benchmark? Active inference, right? Okay. So what is your reference distribution? What is your reference model? And so we are starting some experiments to try to figure this out in a situation where we don't have a natural benchmark like in the case of common filter. So we are not looking at asymmetry like skewness or something like that. We are trying to actually look at portfolio investments. And there we have actually no idea what the reference distribution is of reward or returns that people have when they go into the stock market. And we also expect this to be different from different people, right? So we just need, this is going to be key. It is a bit like in prospect theory, there is an Achilles heel there, which is the reference point. You know, I can explain an enormous amount of things by every time changing the reference point. And this theory is at risk of also explaining everything, because it's up to me as researcher to define what the reference model is, right? And that's of course a very a serious weakness. So we need to get a better understanding as to how this reference model is formed. So far, what I've shown you is evidence that confirms the theory, but that's really not science, right? You want to go beyond that. You want to try to find whether you can reject it in one way or another. But for that, you need to solve this puzzle of how the reference model can be changed actually in people, how you can, with sufficient practice and sufficient latency, can you change people's reference model? And nothing is known about this. As I said, the engineering literature, the engineers think about this very differently, right? Because they're very practical. They have a brake, an anti-lock braking system they need to work, or they have a limb that needs to pick up things from paper to pieces of gold, right? So they can find a reference model that will provide not only robustness, but stability, even if it's just a piece of of paper versus gold, which is, you know, the weight per cubic centimeter is completely different. And it's amazing that when you see these limb works, that they can actually pick up a piece of paper as fluently as a piece of gold. We can do that too, but that's because somehow, in fact, actually, I should have mentioned, in the sensory motor system of the brain, there is actually evidence that the reference models are being used, which may explain why actually we can do things as smoothly in the old robots. You remember Star Wars movies? It was ridiculous how, you know, these robots were moving around like this, right? Couldn't do things. Now you see robots like Boston Robotics has these robots which are unbelievably smooth. They can jump from woods on concrete on carpet and still look like, you know, they understand this. This is reference model based adaptive control. Right? But these guys, the engineers, choose a ball that allows them to be like that. With humans, this is a different matter, right? Yeah, nature can choose whatever they want, right? So, you identify the weakness of the theory, and I shouldn't have, in honesty, have acknowledged, you know, this is the weak part of the theory.
Okay, so one idea maybe is that maybe it is constructed. It's not a stable reference.
No, it is. I am absolutely sure.
Yeah.
You know, if I have to bet on this, it is constructed. And the question is, what are the latencies here, right? How long does it take to adapt people to a particular environment? So that's what the experiment we're running now is focused on, a very, very simple environment, because you want to make it as simple as possible, right? So, you know, my finance colleagues are going to say, oh, these are not very realistic, but, you know, that's the whole point of an experiment, right? What do you want, right? I don't want to have any confounding factors.
Okay, thanks. Yeah.
Very interesting. So coming back to Ori's question and what you spoke about the finance, if I see the stock market going up, the S&P, for example, by 10%, I will be surprised for less time than if I see it going up by, say, 2%?
Yes. Yes. So, no, let's put it this way. The anterior insula, I'm just reading off what the anterior insula is saying. Initially, in the first 400 milliseconds, you pay a lot more attention. That is, the anterior insula signal is an attentional signal, right? So this is how anterior insula is considered. It's part of the attention network in the brain. And when it goes up with 30% or 40%, your gut reaction, this is not gut, is your brain reaction is, I need to pay attention. When it's 15%, okay, well, you know, I expected this. If it's 2%, your initial reaction is, you're not even paying attention. It's actually not on your radar screen, right? It's almost like it's not salient enough. Then after 400 milliseconds, your brain says, wait a minute, you know what? It only went up 2%. Something is fishy here. You didn't pay attention, and you better pay attention to it, right? And that's the significance of that signal, right? So now, of course, this is a task where that's the only thing they have to pay attention to. So it's possible for the brain to do that. You can imagine if there's a lot of distracting stuff going on around you, that signal may just be absent. So again, this is a controlled experiment. But this is how you have to look at this. People like to be in a quiet place, and a quiet place allows you to quiet down. The noradrenaline in your brain, or your adrenaline in your body, is going to be quiet down, so it'll be very pleasant. But if it is too silent, you start thinking, oh, wait a minute, you know, am I missing something? I expect shit to happen and it doesn't happen. If I may say this in French. So that's basically how I interpret the brain signal. I have no idea how else you would interpret this reversal, which is extremely significant, right? So if you do the statistical test there, I don't know how else you can interpret that.
This is very interesting, because I think if the stock market goes up by 10%, my first reaction is to tell my wife how much money we made and how smart I was. If it's going up only by 1%, does not matter much. But if it's going down by 10%, I have to close the computer.
Well, to be honest, your wife should say, you know, if it only goes up with 1%, I thought we were going to make some money, right? But it's not going up. It's just the change, right? It's up and down by 1%, right? Your wife should react and said, you know, isn't this strange? Nothing is happening. That's the question, right? Like the silence. One day I was in Hong Kong. There's a typhoon rolling in from the Philippines, and I was flying Lufthansa, and these pilots were very cool about this. And we were the last airplane to leave the airport before the hurricane. You could actually see the hurricane coming towards Hong Kong, right? And in Hong Kong, it was unbelievably silent. There was nothing. It's as if nothing was going to happen, right? And so for me, this was extremely. I of course knew that something was going to happen, but it is an eerie feeling that when everything is silent. Another example of
about 2 weeks ago.
Was that?
Yeah.
I think we experienced it about 2 weeks ago.
Yeah, well, exactly, right. So you guys have a lot of experience with trying to get out of nature. Just what do you expect? You expect a certain level of things that happening, and if that doesn't happen, you also are alert. And robust control of this type actually captures that human behavior. That you know it's in terms of attention, but also in terms of behavior, right? You want to have a certain amount of excitement, right?
Yeah. I have just a comment. It would be interesting to think about the relationship of your results and to our experimental paradigm is much simpler, and we don't look in the brain. But we do have this phenomena that when the results are surprising, and our definition of surprise is similar to your definition, we do see that we have this phenomena surprise trigger change. So in the two-arm bandit paradigm that we study, it's actually it's particularly clear in a simpler setting that when you see the pair from both options, you have to in each trial you have to select between two options, and you get full feedback. You see how much you got, and also you see the foregone. And and one of the results we observed that when the result is surprising, people change. So even if you are positively surprised by your choice, you're moving to the other option. So it's the opposite of what reinforcement learning would predict. And but if you select something and you are negatively surprised, you move to the other one, which is consistent with reinforcement learning.
So Ori, this is
I
think Ori sent me the paper, right? Yes.
Yeah, could be.
It's also included there. Yeah, it's not.
Okay.
It would be interesting to see how, but our model basically suggests that learning is affected by average payoff, but not exactly by reinforcement learning. So it's not a sequential adjustment.
Yes.
But definitely is we still don't. It would be really important to relate these two lines of literatures.
Okay.
Which we have not done yet. But
okay, so I will have a look at this paper to see whether
we should do
nicely
that
with
too.
MRAC. You want to see the opposite as well, right? So you want to see when actually uncertainty is when there is less surprise than what they expect. It will be interesting to find that in the data that they also.
But in our study, when there is less surprise, they are most likely just not to change. And there is also a similar result in the stock market, right? So you probably know much more than me about it.
I think it's pretty easy to imagine a situation in which we do the same experiment in which actually instead of always constant payoffs, you get slight changes every trial, and then when it's suddenly constant, it's definitely going to be a surprise. So it's also going to be surprise trigger change. The surprise can also be, so if you always see 1.3, 1.4, 1.6, 1.2, 1.1, and then suddenly 1.2, 1.2, 1.2, 1.2, 1.2, it's a surprise.
Yeah, but Ori, what's important where MRAC is different from standard account of surprise like the Pearce-Hall adjustment is it's surprise relative to a model. So it's not that it's constant, there is no surprise. If it's constant and you expect variability. That's
Yeah.
surprise,
Yeah,
right? And that's
yeah.
the important thing, right? So there's a negative prediction, and that is where it stands out, and that's what I wanted to show also in anterior insula. Anterior insula, the signal tells you that the brain understands that it expects. As I said, you know, I said it in French, right? You expect shit to happen. If it doesn't happen, you are surprised and you're looking, I don't understand this. Contingencies have shifted, right? And that's the difference between classical accounts of surprise like Pierce Hall and what we're doing. We know Pierce Hall is maladaptive. You actually do Pierce Hall in our old experiment, the experiment that actually I showed here, if you do Pierce Hall adjustment, you're going to do extremely badly in the transitory situation in which the outliers revert, which is the red one here. Right? When you see an outlier, it comes back. It's going to be really, really bad. And people actually do a lot better than that, right? So but they're not doing what they should be doing. Yeah, so I'll look, I'll look at your paper and see whether I can.
Yeah, we should do the same.
Yes, and then see how we can change marginally the paradigm in order to get to this very surprising result. And if actually the surprise is less than you expected, then you're also paying attention. It's not, the thing is, it is a countering act. There is no salience there, right?
Yeah.
And salience is important for attention, triggering attention. Right, so there is, in general, you would expect less effect of surprise at below what you expected, just because it is not salient enough.
Yeah, thanks.
Peter,
Okay.
thank you very much. This was super interesting. You will
Yes, thank you for letting me speak about this.
Thank you. This was
Thanks.
fascinating.
Okay, yeah.
Okay.
Thank you very much, Peter.
Have a nice afternoon or evening
Yes.
now, by now. Okay, bye.
Bye-bye.
Bye.
Thanks.
See you. Thank you.